All right, good morning, everybody. So there seems to be some issues with the recording hardware in the classroom. So I've started a Teams meeting and I'm recording it over Teams. So hopefully this works. All right, so in the last lecture, we were talking about relationship between classes, and we were looking at the relationship called composition. Right, so remember in composition, an object owns another object, right? So inside that object is a field of some other type. Right, and the object has, or so it's supposed to have, exclusive access to the object that makes up the composition. So the example we were looking at was this thing called a period. A period is just a period in time, so it has a start time and an end time. Right, we're going to represent the start time and end time using the date class, and we have this class invariant where the start time is always before the end time, right, which makes sense for a period of time. So we're going to implement we want to implement a composition. So a period is a composition, so that's the solid diamond, of two date objects, right? One for the start time, one for the end time. Okay, and so there's the beginning of our period class, right? We have a date reference called start, and we've got a date reference called end, right? For the start and end time. We looked at so here's the correct constructor, right? This is the constructor that takes in a start time and an end time, right? So remember, when you're implementing a composition, you have to, so in this particular case, we have to copy the input start and end objects before we assign them to our fields, right? So we make a copy of the start time. So there's our start copy. We make a copy of the end time. There's our end copy, right? If the class has, or if the method or constructor has some preconditions, and this one has one, right? Start time must be before the end time. Then you have to validate the copies before you assign your fields. So here we're going to validate, is the start time greater than the end time? So does the start time come after the end time? And if it does, we throw an exception, right? Only if you get past the validation step here can you assign the fields this start and this end. And so now the start time for the class is a brand new independent date object compared to that start time that was passed in, right? And the end time is a brand new date object that is independent of the date object that was passed in as the end time, right? And so whenever you're implementing a composition, there's always this copying that's happening. Okay. So for example, in the copy constructor, if you just wrote this start equals other start and this end equals other end, that's what you would write if you were doing an aggregation. Then you run into a problem, right? So what you're saying here is that the start time of this object is the same start time object belonging to other, right? And the end time object is the same date object belonging to other, right? So you now have two period objects that share the exact same start and end date. Right? What should you do? You should copy the other start time and end time, and then assign the copy to this start and this end, right? So instead of writing this start equals other start, right, make a brand new date that's a copy of the other start time, and make a brand new date that's a copy of the other end time. Question. So what is the point of making the copies, right? So remember, in a composition, you have to make sure in this case, the period object has exclusive access to its start and end time, right? If it doesn't, right, so if you just write that, right, if the other period object changes its start or end time, right, then the start and end time of this period object is the same object, so they also appear to change. Right? So now you have two period objects, but there's really only one, right, because it's sharing the exact same state as another period object. Right? You want them to be two independent period objects. Right? So the only way you can absolutely guarantee independence is by actually copying the date fields here. Right? It gets worse back here. Right? So here's the constructor where someone passes in a start time and someone passes in an end time. Right? So if you just wrote this, right? So this start equals start and this end equals end. Right? Someone can make a period object with this constructor. Right? that caller can then change the start time and end time to whatever they want, right? And now suddenly the periods object start time and end time also appear to change, right? The caller can make the start time come after the end time, and that breaks the invariant, the period class, right? So then suddenly the period object has a start time that comes after the end time, right? Which isn't a valid period of time. Does that answer your question? Oh. If you have accessor methods, so if you have a method that returns the start time or the end time, right, you cannot directly return a reference to the start time or the end time, right? These are all the examples I've been talking about. These are all examples of privacy leaks, right? You're releasing information that you shouldn't be. So you can't just return the start time, you have to return a copy of the start time, right? So return a new date object that's a copy of the start time, return a new date object that's a copy of the end time, right? If you don't do this, right? So again, if you just return this start, then someone can get the caller who gets the reference via get start can now change your period object start time to whatever they want, right? So they can make start time now come after the end time, and again, the class invariant for the period class is broken. If this is all very repetitive, it should be, right? So here's a method that sets the start time. So someone's going to pass in a date object that corresponds to the new start time. Right, so this method appears to, at least the start of it appears correct, right? It validates the start time, the new start time, right? Compares the new start time to the current end time, right? If the new start time is less than the current end time, everything's fine, right? So we assign this start to new start, we set OK to true, and then we return OK, right? Again, this is busted, right? That line right there, right? Simply sets this start to the same object that was passed in, right? If someone changes new start, the start time for the period object changes as well. So the correct thing to do, make a copy of the incoming start time, right? So there's your defensive copy. Validate the copy. Only if the validation succeeds do you assign the copy to the new to your field. Right? This is all very repetitive, right? You just have to remember if there's something that's going to affect one of your fields, right? Then you so for example, if someone's passing in a new start time in this case, right, you have to make a copy of it before you assign it to your field. Right? And so all of those examples I just went through, they're all generalized, they're all specific examples of these things here. Right? If you have a constructor that takes in a y object, this y equals y, that's aggregation, is not composition, right? That's a privacy leak. Right? This y's object is the same y object as the one that was passed in. Right? Here's your copy constructor. Right? This y equals other y, again, privacy leak, right? The y object belonging to this object is now the same y object belonging to the other x object. Get y releases a reference to this dot y. That's a privacy leak, right? Anybody who gets, anybody calls get y gets direct access to your y field. And similarly, if you set y, the method set y, where someone passes in a y object, if you write this y equals y, right? If the caller changes the state of their y object, the state of this dot y also changes, right? So these are all the correct thing to do if you're implementing an aggregation, right? If you're implementing a composition because your class has some sort of class invariant that you need to ensure, these are all probably going to be problematic. Okay, so what happens if you have a privacy leak in a composition, right? In other words, what happens if you have any one of these four? Right? Then a privacy leak allows some other object to control the state of the object that leaked the field, right? So for example, if your period class has a privacy leak in it, then somebody else can change the state of the period object. Right? And that in depending on exactly what the field is being used for, your object state can become inconsistent, right? So in the period class, suddenly the start time can appear after this end time, right? And you now have an inconsistent period object. Right? If you make up an example like credit card, right? Every credit card has an expiry date. So if a credit card exposes a reference to its expiry date, then someone can just take the expiry date and change it, right? Which is probably not good for your credit card. In the case of the period class, right, not only can the state of the object become inconsistent, right, it's impossible to guarantee any class invariance, right? So in the period class, right, the start time and the end time, so the start time can become after the end time, which breaks the class invariant of the period class. Right, and basically, if you have a composition and you have a privacy leak, then you no longer have a true composition, right? So your object no longer owns its own fields, right? If your object goes away, so you're done with the object, then at some point it gets cleaned up, right? Then when that object dies, right, the parts might not die with it, right? So if you leak a reference to one of the internal parts, right, if someone still has a reference to that part doesn't go away when your object goes away. Okay. All right, so if you're implementing a composition, right, you have to be very careful of privacy leaks. That's the point of all this, right? To avoid the privacy leaks, you're making these defensive copies in many places. The problem with making the defensive copies is that it takes time and memory to make the copies. Okay, if you want to make an immutable object, like the string class, right, then there's a bunch of things that you have to do. I think we've seen this slide before, right? So you want to make an immutable object. So what does that mean? You can't change, the user of the object can't change the state of the object. So obviously, number one, you're not going to provide any methods that can change the state of the object. Right? For safety, you should make all your fields final, right? So that means once you assign a value to the field, you can never change it. That's good, right? You want an immutable object. You want to make all your fields private, right? If you don't make a field private, so if you make it public, then some other object can access the field and change it directly, unless it's final, right? And step 5, you have to make sure that if your class has any reference fields, then you cannot leak leak a reference to one of your fields, right? So you have to basically implement a composition in this case. Step 2, we're still not ready to talk about. Or sorry, part 2, we're still not ready to talk about yet. Okay, so far we've looked at examples where you've got an object and it has a relatively simple object inside of it. Now the question is what happens if you have a collection of objects inside of it, right? So like an array, right? So in Java, arrays are reference types. If your class has a field that's an array, then you need to consider whether you should be using aggregation or composition. Right. Now, if you have an array of primitive types, right, that's a lot easier to deal with than if you have an array of elements having reference types. Right. So if you have an array of objects, that story becomes a little bit more complicated, and we'll talk about that later on in this lecture briefly. Okay, so let's look at an example where you have a class. It's got an array inside of it. The elements inside the array are primitive. Right, so I want to implement a combination lock. Right, so combination lock is just so you can imagine one of those cheap bicycle locks that you might have had as a kid. It's got some dials on it. You turn the like 3 or 4 dials, or maybe more. Right, you turn the dials to some digit between 0 or 9. If you get the digits all correct, the lock unlocks. Right, so if you wanted to implement something like this in Java, right, one way to do it would be to create an array of ints to store the combination. Right, so if you've got 4 wheels on your combination lock, you would have an array of length 4. It's a lock, so it can be in one of 2 states. It's either unlocked or locked. Right, so you might want a Boolean field to indicate the state of the lock. All right, so we're going to have a combination lock class. Ignore the implements comparable. Right, that's not important here. Right, what's important here is that you've got a field that's an array, and it's an array of primitive type. Right, is locked is true if the lock is locked, is false if the lock is unlocked. All right, now remember when you have an array, right? So we've got a field here whose type is an array. We don't have an array yet, right? This is one of the most common errors new Java programmers make, right? You have a variable that can hold an array. There's no actual array yet, right? You still have to make the array, right? And so where should you make the array? Well, you make it in the constructor, right? So the no argument constructor makes a combination lock whose combination is 999, right? So you make your array, right? So this combination equals new int 3, right? That's where you make your array. Once you've made your array, you can go ahead and use it, right? So now I can set the elements of the array to 9, 9, and 9. Right? I guess the comment here says the lock is locked, so we set this is locked to true. Okay, now if someone makes a combination lock and passes in a combination that's encoded in an array, right? You have to copy the array. Right. So in this case, someone's going to make a combination lock. They're going to pass you the combination as an array of int, right? You need to make a copy of the incoming array, right? If you don't make a copy of the incoming array, right? So in other words, if you just write this combination equals combination, right? Then whoever's passing in the array can now go into the array, change the numbers in the array, and suddenly your combination lock, its combination changes as well. Right? So if you want the combination lock to control its own combination, you've got to copy the array. Right? The easiest way to copy an array is to use copy of. Right? Now you should do some validation. Right? So if the length of the copy is less than 3, that's a problem, right? Our lock's supposed to have 3 numbers in it. You should check if they're between 0 and 9 because that's the other class invariant that this thing has, right? But I didn't do it here. It doesn't fit on the slide, right? So there should be another validation here that checks the digits of the combination. Right? Only after you've passed the validation can you go ahead and set your fields. Right? So set this combination to the copy, right? Set is locked to true. Right. Again, if this is all repetitive, if this seems repetitive, it's because it is, right? We're making defensive copies where we need to. Right. If you have a copy constructor, well, guess what? You have to make a copy of the other combination locks array. Right. So here I'm going to use constructor chaining to do this. Right. So someone's going to pass in another combination lock. Right. I'm going to call the other constructor to make a copy of this, to copy that locks array. Right. Remember, the other locks array is called combination. Right. So pass the array to the other constructor. The other constructor makes a copy, validates, and so on and so on and so forth. Right. But again, a copy is being made in this step here. Okay. Now here's the other common mistake that students will make when I tell them about, or when they learn about composition. Right. So as soon as people learn about composition, they suddenly make copies of everything everywhere. Right. You don't have to do that. Right. Not every method needs to make a defensive copy. Right. So for example, if you want to unlock the lock, what do you need to do? Right. So the caller is going to pass in an array with I guess a trial combination. You're just going to compare the elements of that array to the combination. If they're the same, you'll unlock the lock. Right. Now notice that the array that comes in, so the combination that's being provided, right, you're not using that to change your combination. So there's no point in copying the incoming array. Right. So for example, right, here's a method. It's being passed an array. Right. If you're not paying attention to what's going on, you'll just copy that array. Right. You don't have to copy that array. Right. You're not using the incoming array to change your field. Right. All I want to do is check, is this combination equal to the combination of the lock? Right. So there's no copying happening here. Right? The copy is not necessary. Right. So you want to avoid unnecessary copying. Right. Again, because every time you copy something, it takes up memory and time. Right. So no copy here. Right. Because the incoming argument is not being used to change the state of your lock anyway. Oh, and that's it. All right. So if you have an array, it's all the same, an array of primitive values. It's all the same thing as if you had any other reference type as a field. Right. It gets more complicated if your collection is not a collection of primitive type. Okay, so what happens if your class has a collection of a field? So for example, your class has a list in it, or a set, or a map, or an array of elements of non-primitive type. Right, and this happens all the time, right? You'll implement a class, your class is managing multiple objects, right? So you want a field that can hold the multiple objects. Right. So for example, most universities have more than one faculty, right? Most faculties have more than one department. So it looks like if you're going to implement a university class to model the way a university works, right, you're going to have like a list or a set of faculties, right? And each faculty is going to have a list or set of schools and departments, so on and so on and so forth. Right. If you're making a class to represent a receipt that you might get when you buy something, right? That receipt probably has some collection of items on the receipt. Contact list on your cell phone, right? It's got a list, contacts, right? And so on and so on and so on, right? You can keep on going over and over, right? The example I'm going to use in the slides is this thing called a polygonal model, right? A polygonal model has a collection of triangles. Okay, so I haven't told you yet what a collection holds, right? So an array, a list, a set, a map, right? The collection, they hold references to objects. It does not hold the objects themselves, right? So this doesn't matter if it's an array list, any other kind of list, any map, any set, right? It's all the same thing. So here I'm going to make an array list of dates. I'm going to add 3 dates to the array list, right? So add D1, D2, and D3, right? What exactly is going on here, right? So the caller has a list of dates, right? So that's your list, right? The list lives at address 200. So you go to address 200 and there's your array list, right? Now your array list object has a bunch of stuff in it. I don't know exactly what's there. D1, D2, D3, these are our dates, right? So D1, there's some object at address 500, right? D2, there's some date object at address 600, right? D3, there's some date object at address 700, right? Those objects are not in the list, right? Instead, what's in the list are the reference to that date object, right? There's a reference to the second date object, and there's a reference to the third date object. Right? The date objects are somewhere else. They're not in the list itself. Right? So your collections, they all hold references to objects. Right? They don't hold the objects themselves. Right? So for example, I have an array list of points. Right? I make a new point whose coordinate is 0, 0. I add the point to the list. Right? I take the point and I change its x coordinate to 10. Right? If I print out the point P, you're going to get 10, 0, right? So it's either C or D. If I ask the list for the first point in the list and I print that point, right? What do you get? Well, you also get 10, 0, right? This point P, which was added to the list, right? P and points get 0. They're both the same reference, right? They're both references to this point that was made there, right? The list holds a reference to the point, right? It doesn't hold the point object itself. So if someone changes the state of P, then as far as the list is concerned, its first point has also changed, right? Because it's the same point, right? So you get 10, 0 and 10, 0. I really want to do this. Oh, skip this course. Skip this slide. This is the slide I want to talk about. So what I want to, I'm just using this as an example, right? We're not actually going to implement a full polygonal model class, right? Oops, sorry. Right. So I'm going to create a class called polygonal model. It's an aggregation of 0 or more triangles. Each triangle is an aggregation of 3 or more points. Right. Now this is 3D, so I'm using 0.3 instead of 0.2. Right. It's not important. Right. All that's important is that a triangle is an aggregation of 3 points, and a polygonal model is an aggregation of a bunch of triangles. Right. Polygonal models are used in computer graphics all over the place. Right. So this image here, which comes from a 3D game, right? The actual objects that are being drawn, they're just made of a bunch of triangles. Some of the triangles are really big, right? So notice that triangles that make up the ground are very large, right? Some of them are smaller, but they're still relatively big, right? And so that ball and that apple, oops, sorry, right? They appear to be round, right? Even though they're made up of a bunch of flat triangles. So part of one aspect of computer graphics right, is how do I make something that's made up of a bunch of triangles, right, actually looks smoothly shaded, right? If you take CISC124, you'll find out all about how that happens. Okay. But these are, sorry, these are all examples of polygonal models. Okay. So all that I care about is that our polygonal model had, a list of triangles. Right, that's all that's really important here. So our no argument constructor, it does the usual thing, right? It initializes this field by making a new array list of triangles. Okay. We've got a clear method, so clear removes all the triangles in the model, right? A list has a clear method, so if you want to clear all the triangles, you just ask the list to clear all of its triangles, right? We have a size method, so that's the number of triangles in the model. A list has a size method, so we just ask the list for the number of triangles in the list. Okay, now, as soon as you create a class that's got a collection in it, right, and it's a collection of non-primitive type, you now have an ownership question that you need to answer. Right. So, does X, is it going to own its collection, or is it willing to share its collection? Right. If it owns it, you have to use composition. If it shares it, you can use aggregation. Right. Now, there's a problem, right? The collection has a bunch of stuff in it too. So, if X owns the collection, does X also want to own the objects that are inside the collection? Okay, so we're going to do aggregation first. So X shares its collection. X is willing to share its collection. It doesn't matter if it's with other X objects or not. Right. So if X is willing to share its collection, right, then you don't have to worry about making a new list every time. Right. Similarly, you don't have to worry about copying the triangles in the list either. Right. So for example, if I implement the copy constructor for polygonal model, right, I can just write this trie equals other trie. Right. And now you have two polygonal models. They're sharing the exact same list of triangles. Right. If one model changes its list, the other model sees the change in the list. Right. If you want to give somebody back a list of triangles in the model, right, the class is willing to share its list, so it just returns a reference to its list. Right. There's nothing wrong with doing it this way. Right. Okay. So what happens if you look at the memory diagram here? Right. So here we're going to we have an existing polygonal model P1. So P1 is a polygonal model. It lives at address 200. So you go to address 200. Right. Inside the polygonal model, there's a list of triangles. Right. That list lives at address 700. So there's our list of triangles. Right. Inside this list of triangles, it looks like there are at least two triangles, probably more. Right. So one of the triangles is at address 1000. The second triangle is at address 1100. When you use that copy constructor that we just wrote, right, you get a new polygonal model. So there is a second polygonal model object, right? But it shares its list with the other model, right? So in other words, its list is exactly the same as the other list, which is that list right there. Okay, so I make a copy. I use that copy constructor, right? So P2 is a copy of P1. P1 and P2, they're sharing their lists, right? If P2 clears its list, right, what happens to the size of P1? Right. Well, so the P2 size is definitely 0. What's P1 size? Well, they're sharing the list, so P1 size is also 0. Right. It's not 100 anymore. Right. So in this case, a change in one of the models, in this case P2, right, produces the exact same change as far as P1 is concerned. Right. All right. So suppose you don't want that to happen. Right. So you say, well, look, I didn't want that to happen. Right. I want P2 to still, I want P2 to have no triangles. I want P1 to still have 100 triangles in it. Right. Okay. So now you have another story. Right. So now you want one polygonal model to own its collection. Right. You don't care about the triangles in the collection though. So if X owns its collection, but not the objects in the collection, right, then you can then the copy constructor in this case has to perform what's called a shallow copy of its collection. Okay. So a shallow copy of a collection means you create a new collection, but you don't copy the elements. You don't make new copies of the elements in the collection. Right. So now you've got two collections. The elements inside both collections are all the same, right? They all refer to the same objects. Right. So the references in the collection are just aliases for references in the other collection. Okay, so we want to implement. We want to change the polygonal model class so that it owns its list, but it doesn't own its triangles. Right. Now notice that when I draw the UML class diagram, right, I'm not drawing the list itself. Right. So what I'm saying is a polygonal model is a collection of triangles, right? 0 or more triangles. We're not saying a polygonal model is a composition or an aggregation of a list, right? So normally, if your class has a collection of stuff in it, like an array or a list, right, you don't show the array or list. Instead, you show the object or objects that are inside the array or list, right, or that are held by the array or list, right? So a polygonal model is it's still an aggregation of triangles, right? It's not a composition of triangles. It's still an aggregation of triangles. So in other words, we're still willing to share our triangles inside the model, right? But I'm not willing to share the list that holds the triangles. So if you want to make a shallow copy of a list, you just use the copy constructor for the list, right? So the hard way to do it, I would like to make a shallow copy of a list of dates, right? So dates is a list of dates, right? The hard way to do it is to make a new empty list and then to write a loop and add every date that's in dates to the copy. Right? So yes, you can write it this way. It's much easier just to use the copy constructor for the list. Right? So if you make a new array list passing in a collection of some kind, right? The way the copy constructor works is it makes a new list and then just adds the references that are in this list to the new list. Right. List and set, they all have constructors that take in another collection as a parameter. Right. So you can make a copy of a set and store it in the list. You can make a copy of a list and store it in the set. Okay, so we've changed our implementation a little bit. Right. So we're going to rewrite the copy constructor so that it makes a new list, right, by shallow copying the other polygonal models list. So now our memory diagram changes. Right. So P1, that's this model here. Right. P2 is a new model, so it's here. Right. Inside P1, it has a list. Right. So there's a list there. Now, inside P2, there's a different list. Right. So it's no longer the same list as the first model, right? It's its own independent list. So there's a second list now. But when you look inside the lists, right, they're identical. Right. So triangle 1, right, is in this list, and it's also in this list. Right. Triangle 2 is in the first list, and it's also in the second list. Right. So again, our two models, even though they have independent lists, they actually have the same triangles. Right. So neither model owns the triangles that are in them. All right. So using our brand new copy constructor, we make a copy of P1. P1 has 100 triangles in it. Okay. Now, when I clear P2, right, P2 size is obviously going to go to 0. Right. P1 size doesn't change. Right. It's still 100. Right. It doesn't change, right? Because when you ask P2 to change its to clear its list of triangles, right, it's the list at address 800 that clears out its triangles. Right. So these disappear. Right. The list at address 700, it keeps its triangles. Right. So the first polygonal model still has references to the triangles. Okay, so again, we use our new copy constructor to copy P1. if I get the first triangle from P1 and I get the first triangle from P2, right? And asked, are they the same triangle? Right, the answer is true. Right, so the first triangle in P1 is a triangle at address 1000. Right, the first triangle in P2 is the triangle at address 1000. Right, those are the same triangle. Right, so this is true here. Right, so we're still in the situation where the polygonal models are sharing triangles, they're just not sharing their lists. So what's the next step? Right, so the next step is, well, X owns its collection and it wants to own the things inside the collection. Right, this is where you have to make what's called a deep copy of the collection. Right, so a deep copy of a collection means you make a new collection and you copy everything inside of the other collection and store the copies inside the new collection. So now we really do have a composition. Right, so a polygonal model is a composition of a bunch of triangles. Right, it's going to own the triangles. Right, our polygonal model wants to own the triangles that are inside of it. Okay, so how do you perform a deep copy? Now you have to write the loop. Right, there is no built-in way to make a deep copy. That's all I want to say about that for now. It's a little bit more complicated than that. So to make a deep copy of this list dates, you have to make a new list. Right, you then have to iterate over dates. Right, and make a copy of every date that's inside that thing, inside that list. Right, so for each date inside that list, make a copy of that date, add the copy to the new list. So that's how you deep copy a list of stuff. Okay. So going back to our copy constructor, right? If we want a composition of triangles, you now have to do a deep copy. Right, so make a new list, iterate over the other triangles, iterate over the triangles in the other model. Every time you iterate for each triangle, you make a new copy of that triangle and add that to your list. Okay. Now, when you look at the memory diagram, things have changed again. Right, so there's model 1, there's model 2. They have their own lists. Right, so there's list 1, there's list 2. Look inside the lists, right? So triangle model 1 has the triangles at address 1000 and 1100. So there they are. Right, now model 2, its list has references to different triangles. Right, so they now live on the next slide because I can't fit them in on the first slide. Right, so now you've got 4 triangle objects. Right, 2 lists and 2 polygonal models. Okay, so again, P1 starts out with 100 triangles. We use our third copy constructor to make a copy of P1. Right, we take P2 and clear the triangles from P2. Right, the size of P2 is obviously 0. Right, size of P1, well, it's still 100. Right, because P1 has its own independent list. Okay, use the copy constructor. Ask model 1 for its first triangle. Ask model 2 for its first triangle. Right, are they the same triangle objects? No. Right, it's definitely false. Are the triangles equal? Yes, they're equal. Right, go back to the picture. Right, so is the first triangle in this list the same as the first triangle in this list? Right, are they the same object? Well, the answer is no. Right, that's the object at address 1000. That's the object at address 2000. Are they the equal triangles? The answer is yes, right? Because we made a copy, right? Because that thing there is a copy of that triangle there. So they're equal, they're just different objects. Right. All right, so notice that in composition, right? As soon as you have a composition of a, as soon as you have a class that has a collection, right? If you want to implement a composition, right, you're now, you have to ask yourself, what is it a composition of? Right? Is it a composition of the collection, or is it a composition of the things inside the collection? Right? If it's just a composition of the collection, right, then you can just use then you just have to make a new list, a new collection but you don't have to copy the stuff inside the collection. Right? If you want to own the stuff that's inside the collection, now you have to copy the collection and everything that's inside of the collection. Right? So you need the deep copy in the second case. Right? You can keep on going further and further and further. Right? So imagine you have a class, it has a collection. That collection is a collection of other collections. So now you have to ask yourself, do you own the collection? Do you own the elements that are in the collection of collections? And so on, and so on, and so on, and so on, right? There's no fixed end to how far you have to go when you, if you're trying to copy something. All right, so that's all I think that you need to know about composition. Does anybody have any questions about composition versus aggregation? All right. Do I have, sorry, I just want to check if I have the slide. Interfaces, yes. Okay, so we're still talking about relationships between classes because there is one more relationship that we need to talk about. All right, we're not quite going to get there today, right? But this is a lead-in to the last type of relationship that we're going to talk about. So we're going to talk about interfaces. Right, so remember what an interface is. You've seen them already, right? So an interface is just a specification of the methods that a class must provide, right? So in other words, it's just a bunch of methods that there's a bunch of method declarations. They have no implementation, right? Now, so for the interfaces that you've seen so far, it's just a bunch of non-static methods. You are allowed to put static methods into an interface, right? And you're allowed to put these things called default methods into an interface, right? So both static and default methods, you have to provide the implementations inside the interface, right? For all of the regular non-static interface methods, you don't provide an implementation. So we'll see an example of these later on. All right, so remember that an interface is also a type in Java, right? So list is an interface in Java, right? So I can use it as a type, right? I can store anything that implements the list interface in the variable t, right? So array list implements the list interface. So I can store a reference to an array list in T, right? Linked list also implements the list interface. So I can store a reference to a linked list in T. You can make your own list class called myList. As long as it implements the list interface, you can store it in T. To implement, if you create a class that implements an interface, right, it's the job of the class to provide all of the methods that are in the interface, right? So with the comparable interface, right, we saw that you had to provide a compare to method. All right, so I want to talk about, let me give you an example of another interface you might want to create, right? So in CISC121, you should have learned about sorting, right? You should have learned that there are multiple different sorting algorithms, right? So it's possible to create an interface, an interface called sort. Sorry, let me just fire up Eclipse. And I'll just quickly make the interface here. All right, so the idea here is I'm going to make an interface called sort. It's going to have one method in it. Oh, here it is. Oh, this problem. Oh, this is going to be fun. So yes, I'm now stuck in this problem where I have to move a window that's off my screen. Come back. Oh, I see what's up. Okay. That's not what I want you to do. Well, this is unfortunate. All right, I guess we won't do that in Eclipse. Sorry about that. This happens when I plug my computer into another monitor and then move Eclipse over to the other monitor. As soon as you unplug the other monitor, it forgets where it is. Thank you, Windows. Okay, so what I want to do is the following. I'm just going to insert a new slide. So what I wanted to do is is the following. Just go. Okay, so I want to make an interface called sort. Public interface sort. Right now, remember an interface, a simple interface is just a bunch of methods, right? They have no implementation. So I want a method that will sort a list. We'll just do a list of integer for now. Later on, you'll see how to generalize this. Right. So there's my interface. It sorts that list T in place, right? So in other words, it changes T so that the elements are sorted. Right. Once you make your interface, you can then go ahead and create a class that implements the interface, right? So I can, for example, public class. You probably learned insertion sort, hopefully. Public void sort. So you provide an implementation of the method that's in the interface, right? So I now need to provide a method that can sort this list T, right? So insertion sort algorithm goes here. Right? And then you can do the same thing for some other type of sort. So merge sort goes here. Right? Again, you provide an implementation of the method sort, and your merge sort algorithm goes here. Right? And so you can have multiple different sorting algorithms. Right? They all have the same interface. Right? In other words, they all implement sort. Right? And inside, and you'll know that every one of your classes will have this method called little s sort that takes in a list of integer and sorts that list. Right? Now, why would you want to do this? Right? Because insertion sort is faster than merge sort if the list is short. Right? If the list is long, then merge sorts can be faster. Right? O log n, O n log n, right? Versus O n squared. Right? But n has to be relatively large before merge sort is actually faster than insertion sort. Right? And so you can have multiple different implementations in this case, of an algorithm, right? And then the user can pick which version of the algorithm they want to use for their particular purpose, right? There's a whole bunch of other types of sorts that you never learn about in 121, right? There are ON sorting algorithms, but they only work under certain specialized cases, right? And so you might provide a class that provides one of these ON algorithms that can sort, right? If the user is in one of these situations where they can actually use that algorithm. All right, so I guess we'll stop there. We'll look at the iterable interface and how to implement that in the next lecture. Now, did this stop recording? I bet you this stopped recording. Where's